Hello, welcome back to Cartography. This is Dr. Lee. This lecture helps you explore basic concepts of isomorphic mapping and the common types, as well as the elements. From our textbook, this is for Chapter 9. Let's begin. Isomorphic mapping will enable you to visualize the three-dimensional volume data using quantitative lines, or line symbols to be exact. In other words, lines with a certain values represent the surface of the specific geographic phenomenon. Somehow, by doing so, actually we are translating the three-dimensional volume data into a two-dimensional flat surface. We called this a planimetric graphic representation of the surface. Surface here is a continuous uppermost layer of the volume data that represents the actual phenomenon. So the quantitative line symbols that are connecting, later we'll call this threading. The same data values are called isolines. These isolines then effectively portray the surface. So let's look at the sample map. Here, lines are connecting the same values for the maximum average high temperature in the state of Ohio. Isolines that are presenting temperature are called isotherm. Again, the map visualizes the continuous surface of temperature data in Ohio. You can notice the gradual change or gradient for temperature, and these changes don't occur synchronously with the county or any administrative boundaries. There are two types of isomorphic mapping. First, isometric mapping, and the second, isoplathic mapping. The main difference here is where the data is measured or collected. Isometric mapping is allowed to represent the data that occurs at points. For example, precipitation gauge data, average temperature data, or sample elevations are taken or collected at these control points. Even though the data is collected at a point location, these control points are utilized to compose a continuous data surface. Imagine collecting the precipitation or temperature data. How many sampling locations would you need for this continuous geographic phenomena? Infinite numbers. Infinite numbers. So that is why the isometric maps use data occurring at control sampling point. Next, the isoplathic mapping utilizes data that occurs not at a point but over geographic areas. Yes, it might be confusing since these geographic areas have distinctive boundaries and it means they are discrete. However, the geographic phenomenon we are trying to represent is actually continuous. For example, population density occurs continuously over the space, just not directly observable. Can you actually see the population density of a county? No. So for that type of geographic phenomenon, we can use the aerial averages to show the pattern. Then, how would you create these seamless, continuous surfaces from the discrete geographic units? Brilliantly, these aerial averages, such as population density per county, are assigned to arbitrary control points. The most popular control point in isoplathic mapping is a centroid. I will explain it in further details later part of this lecture. Now the data is mapped at control points even though they are arbitrary, isoplathic mapping eventually becomes isometric mapping. Here is the example of centroids. For each polygon enumeration unit, these points are the center of gravity of distribution. So in nature, the centroids are not uniformly or evenly distributed over the space. I have explained what isorhythmic mapping is. Then when do you have to select the isorhythmic method? For which geographic phenomenon specifically? First, as we discussed previously, the data must be a geographic volume that has continuous surface. This surface bounds or connects the data volume. Second, naturally, isorhythmic maps effectively visualize the data that is continuous in nature. The map example shows the surface continuity of terrain elevation in Redstone, Colorado. So it is quintessential for a cartographer to fully understand the nature and distribution of the geographic phenomenon being mapped. So this cartographic method is quite useful to show the total form or general pattern of a spatially varying phenomenon, just compared to core plus maps, particularly for an enumeration unit. Local variation within the enumeration unit hardly shows. However, its rhythmic maps effectively visualize such variations over the space. Also, since its rhythmic maps utilize the observable or arbitrary control points, maps are proportionally correct and measurable, easily differentiating the variation while graphically pleasing. Depending on varying intervals, its rhythmic maps can show different levels of generalization. For example, if an elevation map using contour lines as the isolines has a 10 feet interval, that terrain map would show the elevation variation in much detail and greater precision than one with a 100 feet interval. Of course, 500 feet interval will show much generalized terrain variation when compared to 100 feet interval map. No worries. Computerized systems like ArcGIS Pro or ArcGIS Online can draw these maps fairly easily and efficiently for varying intervals. Fantastic. So far, we have learned what isrhythmic method is, two types of isrhythmic maps depending on data collection, and when to use this method. Next, we will continue our discussions on the elements of isrhythmic method with a particular focus on interpolation and design principle. If you have any question about the content from this lecture, feel free to contact your instructor for help. See you later.